In this online lecture, we are going to study about calorimetry calculations. This is part 2 of my thermochemistry series. For for studying or reviewing the assumptions that are made in calorimetry calculations, you can go ahead and check the part 1 of this video. Now here we are going to study about the thermal energy, which is denoted by Q. It depends upon three factors. First is the mass of the substance. Okay, now let's say I have three beakers, and in three beakers I'm heating the substance, and then I have here 5 gram, 50 gram and 500 gram of the substance. Now if I'm giving the same amount of energy, it will take different amount of time to heat each of these three beakers. So the energy absorbed by these substances directly depends upon the mass of the substance. Second, Q depends upon the specific heat capacity, which is denoted by the symbol C, the lowercase c. For this, we studied about specific heat capacity in our previous online lecture. The specific heat capacity, if you want to understand about it, let us suppose we have a beach. On that we have hot sand as well as water. Now there is sun because it is sunny day. It's a sunny day. Now sun is heating both water as well as the sand equally, and then you will experience that sand is much hot as compared to the water. Now what makes the difference here? The specific heat capacity C. So the specific heat capacity C for water is 4.18. However, for sand it is pretty low. Okay, so here sand will easily get hot because the specific heat capacity C value is lesser. So it requires lesser number of joules to heat 1 gram of substance or to raise its temperature by 1 degree Celsius. However, it requires more joules to heat 1 gram of water or to change its temperature by 1 degree Celsius. So Q directly depends upon C, and the third factor and the last factor is delta T. Delta T is the change in the temperature. Delta is the Greek symbol that is denoted to signify the change. Now by delta T we mean the temperature difference. So temperature difference we denote it as T2 minus T1, or you can also write T final minus T initial. So what are these two values? At what value we started and at what value we are finishing? So the pace at which your substance is getting cool or getting warm, that directly affects the thermal energy Q value. So combining these three factors, the first factor which is mass, the second factor which is C, and the third factor which is delta T, we derive the formula that Q is equal to mc delta T. Now in our calculations we are going to use this formula very frequently. Now moving on, we want to understand about the signs of Q value. So I will write here signs of Q. So Q can be positive, Q can be negative. These two possibilities are there. Now to understand about Q values, what does positive value means and what does negative Q value means? Now let us suppose we have this chemical system here, and then we have the surroundings here. Let us suppose the surrounding is water for this chemical system. This is water, so I will just write H2O. These are the surroundings. And then we have this thing insulated. Okay, so we have an insulation here. So this is a isolated system. Okay, so this is your insulation. Now, what does a Q value, positive Q value mean? Positive Q value means Q is equal to positive. That means heat is flowing towards the chemical system. Okay, from the surroundings towards the chemical system. So heat is being absorbed by the system from the surroundings. Okay, that means this process is endothermic. If you recall from the previous lecture, endothermic reactions are those reactions which absorb energy from outside to proceed. So, when the heat is flowing from the surroundings towards the chemical system, that process is essentially endothermic. And what will happen here? As a result, the temperature of water will decrease. So, temperature of the surroundings, in this case we have water, it will decrease because the heat is flowing from the water towards the chemical system. Now, what do we understand by Q negative value? Q is equal to negative. So, which means heat is flowing from the chemical system towards the surroundings. So, this is Q negative. Less than 0 means it's negative. Here it is positive. Q is greater than 0. So, this is denoting the flow of energy. So Q is less than 0, that means it is negative. So here, if you recall the definition of exothermic reaction, so this is what exothermic reactions work. The heat, they release heat to the surroundings. Okay, so Q value is negative, and in this case, what will happen to the surroundings? So temperature of water, which is the surrounding here, it will increase. It will increase. Now this is about the signs of the Q. And also, we want to learn one more thing about Q is that energy can neither be created nor be destroyed. So, the thermal energy, which we are talking about here, which is Q, it can also be neither created nor destroyed. So, that means the Q of system, the thermal energy of the system, plus the thermal energy of the surroundings, I will write SURRO, their sum should equal to 0. This is in accordance to first law of thermodynamics. Q surroundings plus Q system is equal to 0. And if you go ahead and rearrange this formula, you can also come to this conclusion that Q system is equal to minus Q surroundings. Okay, so this is what we wanted to know about Q. Now let's try to solve one question based on these formulas, or let us try to employ these concepts in a problem here. So problem 1, a student places 50 ml of liquid water let me try. A student places 50 ml of liquid water. Let's say we have this question right in front of us. A student places 50 ml of liquid water at 21 degrees Celsius into coffee cup calorimeter. She places a sample of gold at 100 degrees Celsius into the calorimeter. The final temperature of the water is 21.33 degrees Celsius. The specific heat capacity is given, which is 4.18 for the water, and the density of water is given, which is 1 gram per ml. So what we have to calculate is the quantity of thermal energy Q, which is absorbed by the water in the calorimeter. So first of all, we will write down what things are given here. So given is volume of water, which is 50 ml, and then we have the specific heat capacity value 4.18. Then we have density of water, the D, which is 1, and then we have initial temperature, T initial, which is 21 degrees Celsius, and then we have final temperature also, T final, which is 21.33 degrees Celsius, right? So these are the things that are given to us. What we want to find is Q. So what is required? I will just write here required is Q. Okay, required is Q. Now we know the formula. Q is equal to mc delta T. I'll write it nicely. Q. So the formula of Q we just learned is mc delta T. Okay. Now delta T we can easily calculate. So delta T is T final minus T initial, right? So final is given, initial is also given. We will just plug in the values 21.33 minus 21 degrees Celsius, which is 0.33 degrees Celsius, right? So this is the delta T. What else we want? C. C is also given for water. And then M. How do we find M here? So volume is given and density is given, right? So this volume is given here and then the density is given. Now, if you can recall from your previous knowledge, mass is equal to volume times density, right? So this is the formula we are going to use to find M. So volume is 50 ml, and then we will go ahead and put the values. So let me write it again. 50, so 50 volume times the density, which is 1 grams per ml, right? So this is 1 gram per ml, and this was in ml, right? So this ml and this ml will cancel. So what is the mass here? 50 grams. Now let's go ahead and calculate Q. So Q is equal to mc delta T, and from our formula, mass is 50 grams. From our calculations, C is 4.18 and delta T is 0.33, right? So this is what we have found. And if you go ahead and put these numbers in the calculator, so Q will be equal to 69 joules. Okay, so this is the energy that water absorbed. Okay, so since the temperature in the water is increased, okay, so the temperature of water is increasing. So what do we understand by that? So water will absorb the energy, right? And therefore Q is a positive number, right? So we understood that Q is a positive number. So by positive means water will absorb the energy. That's why also the temperature of the water increases. Now this is a solution to this problem. Let's go ahead and do second question on the same topic. This is a question number 2. Let's start to work on this one using the value Q from the previous question. Calculate the specific heat capacity C for the sample of gold if its mass given is 6.77 grams. And what we have to assume is that the final temperature of the gold sample was the same as the final temperature of the water in the calorimeter, right? So let's go ahead and write what's given here. Let's pick the information. So what's the mass of the gold? So first of all, we are given the mass of the gold. So gold has the symbol AU. It's 6.77 grams. And then you have Q here, the Q value, and that's given. So he told that you have to use it from the previous question. So we just calculated it was 69 joules. And what else is given? T initial, TI. It is 100 degrees Celsius, right? And then what is T final? It is 21.33 degrees Celsius. So what we had assumed is that the final temperature of the gold sample was the same as that of the final temperature of the water. So we know that was 21.33 degree Celsius. And now initial was given in the previous question. Initial was given 100 degrees Celsius in the previous question. Now what we require is C. Okay, so I will write here what is required is C value for gold, right? Now we already know this formula, which formula to use. Q is equal to mc delta T, and we want to find C. So we will use C is equal to, we will rearrange this equation, Q upon m delta T, right? So let's see what is given. Let's go ahead and try to calculate delta T here first of all. So delta T is equal to T final minus T initial. So what is my final value? It's 21.33 and minus 100. So this will give me, if you go ahead and put it in the calculator, it will give you 78.6 degree Celsius value. Now the next thing is the Q value. Okay, so Q value for the gold sample. Uh, so from the previous question, if you recall that 69 joules was the number, the thermal energy that was absorbed by the water, which was surroundings, right? The quantity of the thermal energy lost by the gold must be of the same magnitude, okay, but it should be opposite in sign, okay. Since the water absorbed the energy, it was released from the gold, okay, so it should be same in magnitude but opposite in sign, okay. Since it lost the energy, so Q will be equal to minus 69 joules, okay, for this formula. And then what is M? M is already given to us, okay, so we will put the values here which we just calculated. So Q is negative 69, okay, and M is 6.77 grams. And then what is delta T? Negative 78.67, okay. So this is our formula here. Now if you go ahead and put it in the calculator, so you will get the number 0.13 as the answer. So the units will be joules per gram per degree Celsius, okay, grams per degree Celsius. So this is how you calculate the C value for the gold in the calorimeter, okay. Now let's try to do another problem which is based on thermal energy transfer during a neutralization reaction. Let's go ahead and try to solve this problem here. So this is a neutralization reaction. So what is happening here? Where a 50 ml sample of 1 mole per liter aqueous solution of HCl was mixed with 50 ml of 1 mole per liter aqueous solution of NaOH at 25 degrees Celsius in calorimeter. So we mix HCl and NaOH at 25 degrees Celsius. After the solutions were mixed by stirring, so what was the final temperature? 31.9 degrees Celsius. So what do we need to find? A. Determine the quantity of thermal energy transferred by the reaction to the water, and then state whether the reaction is endothermic or exothermic. And then B, we have to find state whether the reaction is exothermic or endothermic. Okay, fine. Now let's go ahead, first of all, write what is given to us, and then we'll move forward. So we will write here, let's clear first of all, uh, let's write given. So what's given here is volume of NaOH, which is 50, volume of HCl, which is 50, density of water is 1 gram per ml. We already know, or it will be given in the exam. So T initial, Ti, it was mixed at 25 degrees Celsius. So I will go ahead and write 25 degrees Celsius. And then what else is given? T final. Okay. T final I'm writing is it has TF. Now what is the final temperature? So he is saying it is 31.9 degrees Celsius. Also, after the solutions were mixed, the temperature was 31.9 degrees Celsius. So we will go ahead and write it here. And then specific heat, you already know, we will take it as 4.18, right? Now, what is required here? Determine the quantity of thermal energy transferred. So basically, we have to find the Q. So what is required? It is Q. Now, you already know we are going to use the formula Q is equal to MC delta T. So C is already here, okay. And then what about delta T? Let's go ahead and find delta T. So TF minus TI, this you already know. I have TF right in front of me, 31.9, and I have this TI here, which is 25. So if you go ahead and calculate it, 31.9 minus 25, so it should give you 6.9 degrees Celsius. Now what about M? Mass is left. So delta T is here, C is here. Now what about mass? So mass is Volume times density, this we did in the previous question as well. Now, what is the volume here? The total volume, because we mixed these two, so the total volume will be the sum of these two. 50 plus 50 will give me 100. I hope you understand that. So 100 is the total volume. And then what is the density? So density would be 1. Okay, so 1 grams per milliliter. So milliliter here. So this is in milliliter, and this one is grams per ml. I showed you last time also. Milliliter will cancel. So what is the mass? 100 grams. So we have this all the three parameters with us. Now we will go ahead and calculate Q. So Q will be equal to mc delta T. So we have 100 times 4.18 times delta T, which is 6.9. If you go ahead and put it in the calculator, it should give you 2.9 into 10 to the power 3 joules. And also you can rearrange to write it as 2.9 kilojoules, right? 10 to the power 3 can be written as kilojoules. Now the other question was, state whether the reaction was endothermic or exothermic. Now, because the thermal energy transferred by the reaction to the water is negative 2.9 kilojoules. So if you go ahead and see here, the final temperature, it increased. Okay, now what will happen in this case, because the final temperature is increasing, so we will say that this is a exothermic reaction. So I will go ahead and write, so the reaction is exothermic. Okay, because your final temperature is increasing, and the Q value that is transferred is minus 29, 2.9 kilojoules, 2.9 kilojoules, right? Now let's go ahead and talk about the new topic, which is enthalpy change. Okay, let's go ahead and talk about enthalpy change. So this is a new terminology, enthalpy, and we are going to learn about it. So about enthalpy change, every substance undergoing a chemical or physical change. We talked about chemical, what is the chemical change, what is the physical change, what do we mean by that in our previous online lecture. So every substance that is undergoing physical or chemical change contains a certain amount of thermal energy, okay, that is Q. So the total amount of thermal energy is sometimes also called enthalpy, okay. So the total amount of Q or the thermal energy is also sometimes addressed as enthalpy, which has the symbol H. Okay. Now chemists are yet to find a way of measuring the enthalpy of a given substance. However, we can measure the energy change that occurs in a system during a reaction, and that energy change we address it as delta H. So delta, you already know, it denotes the change. So delta H we can measure using the calorimetry data. So like we used in the previous question, the calorimetry data. Using the same data, we can go ahead and find the delta H value. Now let us examine why this is possible. So chemists have found that as long as the pressure remains the constant, okay. So as long as the pressure is constant, the enthalpy change of the chemical system is equal to the flow of the thermal energy. So as long as your pressure is constant, the enthalpy change, which is delta H, is equal to the flow of thermal energy in or out of the system. Okay, so we can write that delta H is equal to Q system, right? So the thermal energy of the system in and out of the system. So I have put this modulus here, which are these brackets. So it can be positive or negative. You already know the Q value. So for a chemical reaction, the delta H value is given by the equation for H products minus H reactants. Okay, this is what we want to know. Okay, now delta H is equal to H products minus H reactants. When the product of a reaction have a greater enthalpy than the reactants. Now what are we trying to say here? When the products have high value as compared to the reactants, now what will happen? The system absorbs the thermal energy, right? So what will happen? The Q value will be positive here, the delta H value will be positive here. So the system will absorb energy from the surroundings and the reaction would be endothermic. So I'm going to write here, when delta H is greater than 0, that means it is positive. That means the reaction is endothermic, right? The next thing, if your delta H is negative, that is less than 0, that means the reactants have more H value as compared to your products, then delta H will be less than 0, that is negative. The system will release the energy, okay, and when the system releases energy to the surrounding, we call that reaction as exothermic reaction, okay. So for exothermic reaction, delta H is less than 0, and for endothermic reactions, we have delta H greater than 0, okay. Now if you see here, this reaction here, let's say we have this reaction, Mg solid plus 2 H positive ions, they're combining to form Mg2 plus aqueous plus hydrogen gas, okay. Now this is a reactant, these are your reactants and these are your products here. Now if we see a graph between the energy axis and the reaction progress on the x-axis. So let's say this is your reaction progress and this is your energy on this axis, okay. Now what will happen initially, you have your reactants, okay. So high potential energy of the chemical system, so this is your chemical system here, so they will have high potential energy, okay, of the system, chemical system here. And what will happen after some time, it will begin to decrease, right, and it will decrease exponentially, okay, and it will form lower, when these products will be formed, it will be having low potential energy, okay, so it will become low by the end of this reaction, okay, because most of the reactants are being converted into the products. So here you have high potential energy of chemical system. Now on the other hand, if you go ahead and talk about the surroundings, so surroundings, what we have is this is an exothermic reaction, so you must want to know about this. Okay, so exothermic reactions. So exothermic reactions, when initially there are reactants, so no energy is released to the surroundings because this reaction has not proceeded. So initially your surroundings will have low potential energy, or low, better word is low kinetic energy, because energy is flowing to the surroundings. So low kinetic energy of the surroundings, and when this reaction will start to happen, some of the reactants will become products. So what will happen, because it's an exothermic reaction, some of the energy will start to release to the surroundings and this will increase, okay. So the graph will increase as your reaction will progress with time, and what will happen by the end, it will be having, so most of the energy will be released and you will have high kinetic energy here. So I will write high kinetic energy here of surroundings. So this is nothing but just a diagrammatic overview, the graphical representation of energy of this reaction, of this exothermic reaction versus time, a reaction progress, you can say. So this axis denote low kinetic energy of the surroundings. Okay. Now moving on, we have one more term which we call as molar enthalpy change. Molar enthalpy change. Now, molar enthalpy change, what is the symbol? It is delta HR. Okay. And the molar enthalpy change of a reaction for a substance is the energy change that occurs when 1 mole of substance undergoes physical, chemical, or nuclear change. Okay, so essentially we limit the quantity of substance. Okay, the quantity is 1 mole of the substance. So the enthalpy change related to that is known as molar enthalpy change, and we denote it with delta HR. So the units will be, so I will go ahead and write the SI units for delta HR will be joules per mole. Okay, so joules per mole. Now we have molar enthalpy changes for various types of chemical reactions. Okay, so for example, if it's a solution, okay, I will write here types of molar enthalpy change. So there are types of enthalpy changes. You come to know what I'm trying to say here. Types of molar enthalpy change. Delta HR. Okay. And on this side, let's say we have some examples. So the first of all is if your reaction type is solution. Okay. If it's a solution, then the enthalpy change associated with that reaction is known as delta H solution, and we write it as SOL in short. For example, this NaBr is converting into Na positive aqueous ions plus Br negative aqueous ions. The second type of chemical reaction, let's say it's a combustion reaction. Okay, combustion reaction. So the molar enthalpy change, in that case we call it as delta H combustion, and we denote it as delta HC. So you can take any combustion reaction example. So for example, CH4 plus your O2 is becoming carbon dioxide. So methane gas is burning. It is undergoing combustion, and it is becoming carbon dioxide and water. And to balance it, I put a 2 in front of you, and then everything looks good, right? And then next is if your reaction is vaporization reaction. Okay, vaporization reaction. So in this case, the molar enthalpy change that is related to this type of reaction, we write it as delta HVAP. So it is denoted by CH3. Let's say, let's take this methanol here. So this liquid, okay, is becoming gaseous. It is going in the gaseous state here. So this is one of the other examples. Now the next one is formation. Let's say some substance is being formed. So an enthalpy change related to that is given by the symbol delta HF. So you might encounter these symbols on your exam. So I'm just giving you an idea of that. So formation, let's take an example. Let's say your carbon solid reacts with 2 hydrogen plus half oxygen. These coefficients here are for the balancing purposes of the number of atoms, and all of these 3 reactants are combining to give you methanol here, CH3OH, which is liquid. And then this one is neutralization reaction. Let's say I have neutralization reaction. So I'm unable to write here. I will write it here, delta H neutralize, NUT, okay? And I'll just give you an example here, I will write here. So for example, NaOH plus H2SO4, any base is reacting with any acid. And then what you have is this Na2SO4, okay? And then you have water here, okay? I'm not balancing it. You can try balancing it on your own, okay? This is just to give you an idea how different molar enthalpies for different reaction types looks like.